Welcome to OFP 009. My name is Mugumba PM Mugumba. Today we are going to have the knowledge area number 2 of mathematics, the number system, sequence, and the progression. Introduction. We are now familiar with the system of numbers as their properties assist further in understanding their respective behavior. They are acting as an aid to the solution of problems characterized by some unique patterns governed by some rules. It is in the interest of this lecture to investigate the set of such numbers which are normally stated in a certain definite order. Some of the unique patterns. You can find that there are some of the unique patterns are as indicated on my PowerPoint. For example, some unique patterns are 1 times 8 plus 1, you get 9. 1 times 8 plus 1 equals to 9. You may find that 1 multiplied by 8 plus 1 is equal to 9. It is true. Then 12 times 8 plus 2 is equal to 98. 123 times 8 plus 3 is equal to 987, etc. You can find that the pattern is going as 12, 123, 1234, just like that, are numbered in a order in such a way that the first one is 1, the second one is 1, 2, the third one is 1, 2, 3, the fourth one is 1, 2, 3, 4, the fifth one is 1, 2, 3, 4, 5. But in the middle, you can find that number 8 is constant, is common. While on the right hand side of the plus, there are numbers 1, 2, 3, 4, 5. Therefore, we can find that the number which are equal are in a certain pattern like 9, 98, 9, 87, 9, 8, 7, 6, 9, 8, 7, 6, 5. Just like that. Similarly, another pattern, you can find that there is 0 times 9 plus 1, you get 1. 1 times 9 plus 2, you get 11. 12 plus times 9 plus 3, you get 111. 1, 2, 3 times 9 plus 4, you get 1,111. Also, the pattern goes like 0, 1, 1, 2, 1, 2, 3. The number at the middle is constant, is number 9. While on the other hand, the plus is 1, 2, 3, and 4. The equivalent are 1, 11, 111, 1,111. Likewise, you may have another pattern. 1 times 1 equals to 1. 11 times 11, you get 121, which is common. 111 times 111, you get 1, 2, 3, 2, 1. Just like that. So you may find that the numbers on the left hand side of the equal are ascending and after the middle are descending. For example, here you may find that 1 is ascending to 2, 2 is ascending to 3, 3 is descending to 2, and then descending to 1. Similarly, for the fourth one, 1 is ascending up to 4 and then descending back to 1, just like that. Let's see another pattern. Then you can find that if you add a particular pattern of number relating to 1, for example, 1100 and 111 plus 1111 plus 111 plus 11 plus 1, you can get 1, 2, 3, 4, 5. That is another pattern. Also, there is another pattern. Of 2 squared minus 1 squared equal to 2 plus 1 equals to 3. 3 squared minus 2 squared equals to 3 plus 2 equals to 5. 4 squared minus 3 squared equals to 4 plus 3 equals to 7. Up to 10 squared minus 9 squared equals to 10 plus 9 equals to 19. Actually here, you may find that the first number differ from the second one by 1. Just the 3 is differing from 2 by 1, each by 1. When squared, you may find that these numbers are nothing but the set of... Actually, you may find that these numbers are difference of 2 squares. So, in general, we can say that when you have 2 squared minus 1 squared equals to 2 plus 1 times 2 minus 1. Also 4 minus 3 equals to 4 plus 1 plus 3 times 4 minus 3. Actually, 2 minus 1 equals to 1, 4 minus 1 equals to 1. That's why it is remaining as if it is 4 plus 3. That's the logic of difference of 2 squares. That's the concept of difference of 2 squares. Actually, this lecture introduces the student to the general field of number system, which forms the basis of all other sections of mathematics, as will be apparent to successive lectures. The number system. Descriptively, the set of real numbers may be summarized as follows. We have some symbols. W implies the whole numbers. These are counting numbers including 0, like 0, 1, 2, 3, 4, etc. N implies the natural number, counting numbers excluding 0, starting with 1, etc. Z is an integer, positive and negative natural numbers including zeros. For example, dash dash minus 3 minus 2, negative 1, 0, 1, 2, 3, 4, etc. Q is the rational numbers. This can be represented in the form of A, B, which are real numbers and can be terminated or repeated decimals. Coming to irrational numbers, are numbers which are non-repeating or non-terminating decimals. And the R is the real, rational, and irrational numbers as indicated for Q and I above. Orders and the inequalities. For any real number, A, B, C, R, the following relations are true. Either A is less than B, A equal to B, or A is greater than B. In this case, if A is less than B and B is less than C, then automatically A is less than C. This is a translative property. If A is less than B, then A plus C is less than B plus C. This is an additional property. If A is less than B and C is positive, then A times C is less than B plus C. This is the multiplication property. If A is less than B and C is negative, then A times C is greater than B times C. This is the multiplication property. Solution of inequalities. knowledge of order of inequalities and their properties enable us to solve problems on inequalities which may be in one or two variables. So we can solve here inequalities in one or two variables or more than two variables. We are going to another topic which is called mathematical induction. Mathematical induction is a special method of proof which ranks among most important basic tools in mathematics. The principle of induction. Let P be a statement or formula associated with each positive integer. And suppose the following conditions are satisfied. P1 is true. For any positive number k, if pk is true, then pk plus 1 is also true. Then the statement Pn is true for all positive integers n. For example, prove by mathematical induction that 4 plus 8 plus 12 dash dash plus 4n equals to 2n bracket n plus 1. Solution. To prove this, by hypothesis, we let n equals to 1 to be true. If we fit here, number 1 equals to 4 times 1 equals to 4, is equal to 2 times 1 is 2. And the 1 plus 1 equals to 2. 2 plus 2, 2 times 2 equals to 4. This statement is true. That 4 times 1 equals to 2 times 1 times 1 plus 1, 4 is equal to 4. Let us assume it is true for n equals to k. Let us assume it is true for n equals to k. Then you can say that 4 plus 80 plus 12 plus up to 4n equals to 2n times n plus 1. This is the statement number 1. Let us also assume that it is true for n is equal to k plus 1. Then on each n, you put k plus 1. So it will go up to k plus 1. Then 2 will be 2k plus 1 in bracket k plus 1 plus 1. Then it will go like this. So what we are supposed to do to prove that this side equals to this side, we consider the left-hand side as indicated here. Then we start up to this point. This point is similar to this one. Then this point, which is equal to this, is here you replace by k. Then the whole thing is equal to 2k plus k plus 1 plus 4 times k plus 1. Then you open bracket, you find the quadratic equation of 34. Then you simplify and factorize. In the end, you find that it is 2 times k plus 1, k plus 2, which is k plus 1, k plus 2. Similar to the previous one where we started. So the left-hand side is equal to the right-hand side, and hence is proved. Now we are going to have another topic known as sequence of numbers. Introduction. Properties and the behavior of numbers happen to be characterized by some unique patterns governed by some rules. If it is in the interest of this lecture to investigate a set of such numbers which are normally stated in a certain definite order. Definition for sequence in a series. Sequence is a set of numbers stated in a definite order such each number can be obtained from the previous number according to some rule is called sequence. Each number of the sequence is called term. So each number of the sequence is called term. For example, numbers 3, 5, 7, 9, 11, etc. And the 1, 4, etc. The numbers, these numbers are called term. 3 is a term, and the 5 is a term, etc. The sum of terms of a sequence are called series. So the series is an indicated sum of sequence. In other words, we can say a series is an indicated sum of the sequence. There are some unique patterns you may find in general that 1 equals to 1 square equals to 1. If you take 1 with a common different number, which is 2, because the difference here is 2. 1 plus 3, you find equals to 4, which is 2 squared. Then, with a common difference of 2, 1 plus 3, and another common difference of 2 plus 5 equals to 9, which also is 3 squared. You may go like that. In the end, you may find that the result are square of numbers 1, 2, 3, 4, 5, and 6, which are 1, 4, 6, 16, 25, and 36. Also, there is another pattern in which we have 1 equals to 1 times 1 equals to 1 squared equals to 1. 1 plus 2 plus 1 is equal to 4, which is 2 squared. Also 1 plus 2 plus 3 plus 2 is ascending. The number is ascending and then descending. So you may find that is 9, which is 3 squared. Also this number is ascending up to 4 and then descending back to 1. The resulting number is 16, which is 4 squared. So like that, you may find the squares of numbers. Similarly, for power 3, you may find another pattern relating to power 3. So 1 power 3 equals to 1 equals to 1 power 2. If you take 1 power 3 plus 2 power 3, you get 9. 9 equals to 3 power 2. 1 power 3 plus 2 power 3 plus 3 power 3, you get 36 equals to 6 squared. And then we have another pattern which is 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed, you get 100 equals to 10 squared, 15 squared, 21 squared, etc. These are patterns of mathematics in a particular sequence. Now we are coming at the arithmetic progression. Arithmetic progression is a sequence of number that increase or diminish by a common difference d. And this common difference between the two consecutive numbers is constant. The sequence the sequence 5, 7, 9, 11, 13, etc. to 2n minus 1. The common difference here is 2. Is 2 up to the last one. Let us have L be the last numbers, A be the first number, N the number of 10, D the common difference, S the sum. Let the first number be A. The second number will be A plus B. The second number will be, the third number will be A plus D plus D equals to A plus 2D. Another one, the fourth number will be A plus D plus D plus D equals to A plus 3D. The first one, the second one, the third one, the fourth one. You may find that there is a link between the number of 10 and the number indicated here. So, if you are going up to the nth term, will be A plus nth term. For example, when it was the fourth term, it is a 3. When it was the third term, it is 2. So when it is n, it is n minus 1 times common difference. This is the first number. So we can create a formula indicating that the last number equals to A plus n minus 1 times D. That formula you should hold by heart. That formula you should hold by heart. That formula you should hold by heart. That's right here. L equals to A plus n minus 1 times D. Let me enclose in the box. Also, we are going to see the sum. Also, we are going to see the sum of numbers of arithmetic progression. Let the first one, the first number, be, this is the sum, be A. The second number be A plus D. The third one, A plus 2D plus dash dash. Up the last one will be L. Before L is L minus D. Before L is L minus D. And then before L minus D is L minus 2D. Okay? Now, we look at another sum. S. You reverse the first one to be the last one, and the last one to be the first one. Here we are going to have L plus D plus L minus 2D plus dash 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 plus A plus 2D plus A plus D plus A. You see the alignment. You see the alignment. The alignment will be L plus L minus D plus L minus 2D plus just like this. So let us enclose in brackets, enclose in brackets. We sum up. Here we find 2s equals to A plus L Here we are going to have A plus L. D and the negative D vanishes. So here also we remain with A plus L. Here we have A plus L. 2D and the negative 2D also vanishes. We have A plus L. Here L plus A also remains A plus L. D and the negative 2D vanishes. Here also we have A plus L. And here we have A plus L. If there are n terms, we are going to have A plus L times n. So 2s equals to n, which is the number of terms, A plus L. Then the sum is given by n divided by 2, divided by 2, A plus L. This is the general formula of our sum. This is the first formula. This is the second formula. Now, if we include L as A plus n minus 1 times D, we are going to have S equals to n by 2, bracket A, L equals to, from 1, equals to A plus n minus 1 times D. So S equals to n by 2, bracket A plus A is 2A plus n minus 1 times D. This is the third formula which we are going to use. So in general, we are going to use 3 formulas for arithmetic progression. The formula are as indicated. The first one is L equals to A plus n minus 1 times D, as we have proved. The sum of arithmetic progression, as we have proved, that S equals to n divided by 2, A plus L, and all the equals to n divided by 2 to A plus n minus 1 times D. So, we have seen that the last term of arithmetic progression is given by L equals to A plus n minus 1 times D. The sum of the arithmetic progression is given by S equals to n divided by 2A plus L, where L is the last number. If you expand this, you will find that S equals to n divided by 2, 2A plus n minus 1 times D. Now let us go to the example. Find the 10th term of the series, and then find the sum of the first 10 terms. Given the first term is 4, and the common difference is 7. Let A be the first term and the number of terms, D the common difference, and L the last term. S is the sum of terms. Given A equals to 4, D equals to 7, and N equals to 10. The 10th term. Since L is given, then we put A equals to 4, then N equals to 10, minus 1 times the common difference, which is 7. We get 4 plus 63, the 10th term, will be 67. 63 plus 4 is 67. For the sum of the first 10 terms, we find that S equals to N divided by 2A plus L. We can say equals to 10 divided by 2, 4 plus 67, which is 71. So 5 times 71 equals to 355. Otherwise, alternatively, we can use the formula S equals to N by 2 times 2A plus N minus 1D. We can say equals to 10 divided by 2, 2 times 4, 10 minus 1 times 7. Here we have 8 plus 63. 63 plus 8 we get 71 times 5, we get the same 355. Yeah, we are going to have another topic of geometrical progression. Actually, geometrical progression is the one whose next term is obtained by multiplying or dividing with a certain constant number to the previous term. The constant number is called common ratio, R. The common ratio R of geometric progression can be obtained by dividing any term by its immediate predecessor. Let L be the last number, A be the first number, N be the number of terms, R be the common difference, and S be the sum. Be the sum. The first number be A. The second number be AR. The third number be AR times R equals to AR squared. The fourth number be AR times R times R equals to AR per 3. If we are going to, let us do the second one, the power is 1 for the second one. The third one, the power is 2. For the fourth one, the power is 3. If we are going up to the nth term, the power of R will be AR n minus 1. Therefore, we can say the last number of the geometric progression is AR n minus 1. This formula we can keep the top. Now we can say L for geometric progression equals to AR raised to power n minus 1. That's the formula for geometric progression. Now, we are going to look at the sum of the numbers in geometrical progression. Let us have sum S is given by the first number A plus the second number AR plus the third number AR squared plus dash 2 AR n minus 1, the last one. This is equation number 1. Now, we copy the equation similar. S equals to A. The sum of arithmetic progression is given by S equals to A plus AR plus AR squared up to AR raised to N minus 1. Then if we copy again, S equals to A as this, but we shift A plus AR plus AR N minus 1. Just copy. Then we multiply this second sum by R. We multiply this second sum by R. So this will be AR, this will be AR squared, this will be AR N minus 1 up to ARN. This is equation number 2. We subtract equation 1 from 2. We subtract equation 1 from 2. RS minus S equals to this minus this, this minus this, this minus this. We remain with the ARN minus A. We remain with the AR raised to power N minus A. We factorize. We get common here is R. The common here is S bracket R minus 1 equals to A Rn minus 1. Therefore, we divide by R minus 1, we get S equals to A bracket Rn minus 1 divided by R minus 1, where R is not equal to 1. R is not equal to 1. Because if 1 will be equal to 1, the denominator will be 0, which will give undefined. Therefore, this is the formula for the sum of geometric progression. If R is less than 1, for the case R is less than 1, the sum is given as S equals to A reverse bracket 1 minus R power N divided by 1 minus R. Similarly, R is not equal to 1. This is the formula for R if it is less than 1. If it is greater than 1, you use this one. The last term of arithmetic progression, as we have determined, that L is equal to A R raised to N minus 1. The sum of arithmetic progression is given by S equals to A R raised to the power N minus 1 divided by R minus 1, where R is not equal to 1. Because the denominator, if it is 0, it will be undefined. When r is less than 1, you reverse. You say s is equal to a 1 minus r power n divided by 1 minus r, where r also be not equal to 1. The end. Thank you for your attention and your time.